So in this lecture we will continue our description of aerosols, and we will look more in the aerosol dynamics and the deposition process. So when we see the physicochemical profiles of indoor aerosols, the size and chemical composition of the particles generally will evolve with time, and this could be through the processes of coagulation, condensation or evaporation, and then also chemical reactions. So when the indoor in the indoor air the pollutant is emitted, or it's coming from outdoors, they are subjected to different indoor dynamic processes. These could be deposition, coagulation, and then condensation and evaporation. There are many factors that will affect the physicochemical transformation of the indoor aerosol, and these may include the building characteristics itself, such as the volume, so how big a room is or how big the rooms are, what is the surface area available in the room. So actually if there is more surface area, there is more place for the particle to attach to, so more sort of deposition. How are the ventilation characteristics within the room, and what exactly is the wall or the floor surface material itself, and we will a little bit look at all these factors, and they will affect the overall movement and the fate or deposition of particles in the room. Now deposition onto the surfaces is a main removal process for indoor aerosols, especially in the ultrafine and coarse particles, less in the accumulation mode, as we have already seen before. So deposition on surfaces is mostly prevalent for ultrafine and coarse. How? These mechanisms can be a number of them. This could be Brownian diffusion, and we will look at the definitions shortly. Brownian diffusion, turbulent diffusion, turbophoresis, thermophoresis, shear-induced force, electrostatic drifting, and then finally the inertial impaction and gravitational settling. So there are a number of mechanisms which will influence the fate of aerosols in the indoor environment in terms of deposition. Brownian motion is, as we have studied in our schools and other settings, Brownian motion is the random movement of small particles that are suspended in air. So example would be a movement of aerosol particle, and it's colliding with gas molecules which are moving at different velocities in random directions. So the aerosol particle will gather this kind of random direction motion through different collisions. Turbulent diffusion is also diffusion, but it is much faster than the Brownian diffusion, which was due to sort of collision with gas molecules, so to speak. The turbulent diffusion is due to rapid motions of the indoor air masses, so much faster than the Brownian diffusion. Turbophoresis is generally the migration of particles towards decreasing turbulence. So if there is high turbulence, the particles are sort of migrating towards decreasing turbulence. So these are the processes that are there. Not necessarily it means that these are the dominant movement processes, but these are the processes that can potentially influence. It does not mean they are the dominant processes. So an example here is particles in high velocity movements may move towards the wall, because then the wall is a place of decreasing turbulence. We have then the next pathway or the next process is thermophoresis, which is due to which is the transport of particles due to a temperature gradient. So in this case the particles will move towards a lower temperature region. So this is our thermophoresis. The next thing is shear-induced force, which is when the particles are moving in the fluid, there is a sort of a shear force exerted, and this will also influence the overall movement of particles. Then we have electrostatic drifting. So if the particles themselves have some surface charge, for example clay, they will move towards like the opposite charge surface just by the electrostatic drift. Then we have finally the inertial impaction and gravitational settling. Basically, the larger particles, when they are impacting the wall surface or any other surface or any other obstruction, after impaction they will lose their energy, and then once they lose the energy they are going to settle by gravity. So this is our inertial impaction and gravitational settling mechanism. So generally when we are looking at a free moving air, on this side we have sort of the airflow in near the wall. So this is the wall, and this is sort of the velocity, this is the concentration profile here, but also sort of how the flow will look like. So we have the free air here. So now there is some concentration. As we now a particle in this region has to deposit to the wall. So initially advection and turbulent diffusion are the main processes. So in this area we have sort of advection and turbulent diffusion. This will bring the aerosol closer to the wall, somewhere around this region. So now it's like a flux, settling flux. We are in this region where we have sort of this small boundary layer. This is the layer at the boundary, so boundary layer, and there is some concentration here. And so aerosols from the core air are brought towards the boundary layer, which could be about a very few centimeters from the surface. And then this settling flux is going to lead to the settling at the surface, where we will have a concentration in the wall, sea wall. And then this will look as the concentration profile, higher or how high or how low, that depends on condition. But so through advection and turbulent diffusion, a particle is brought towards the boundary layer, and then it goes and settles to the surface. Then particle, once it is in this boundary layer scenario, it is deposited by one of the many processes we have just identified in the or listed in the previous slides. In general, Brownian and eddy diffusion are the most important processes for fine particles. For coarse particles, we are looking at gravitational settling and impaction as the main processes influencing their deposition. Then there are other processes in a regular indoor environment they can also influence, which is one, thermophoresis, so temperature gradients within a room. For example, when there is air conditioning, there might be some temperature gradients. Then electrostatic drifting due to charged particles nearby the surfaces. So and sometimes we have charged particles, and then they will also drift near the surface, and this can also influence the deposition process. Now dry deposition, so basically deposition of our dust particles without the influence of rain or some moisture. So dry deposition, a regular deposition of indoor aerosols, can be described via the concept of a deposition velocity. So if you can recall, in our mass balance lecture, we indeed looked at an example where we had a deposition velocity of some gas, of some chemical or aerosol. So we have a deposition velocity. It will be the ratio of the particle flux to the surface to the particle concentration. So this ratio will basically lead us to the flux deposition velocity. So we will have number per meter square per second, and particle concentration will be divided by number per meter square. So we will have meter per second, or in this case if we are looking at number or mass per centimeter square per second divided by the concentration, number of mass divided by centimeter cube. So we will have a centimeter per second velocity. So let us say we have a flux n per meter square second, number of particles per meter square per second, divided by concentration. So let's say number per meter cube, or let's do centimeter square per second and centimeter cube. So this will be equal to centimeter per second, which is our deposition velocity. So in actual deposition models of indoor aerosols, this deposition velocity can be a function of the particle size and also the fluid friction velocity. In a simple parameterization, a deposition velocity is just given as a function of deposition rate constant. So Vd will be volume of the room multiplied by the deposition rate constant divided by the surface area of the room. So we will have a surface area, and so let's say this is our surface area S and this is the deposition velocity. So this is basically Vd times S is our deposition flux, Vd times S, meter per second multiplied by the meter square area. So this is our deposition flux downwards. This will be equal to a deposition rate constant multiplied by the volume, because this volume of the room, if this is our volume, this volume is swept down at or this volume is sort of depositing at a rate lambda d. And again we can easily match the units, let's say meter. So meter per second times meter square. So this is meter cube per second. This is 1 by second multiplied by meter cube. So both sides are meter cube per second. So we can easily match dimensionally and confirm this derivation. So this is sort of the flux, deposition flux, and this will help us derive a deposition velocity Vd. For particles more than 0.5 micrometer, it is generally found that this deposition velocity is independent of the ventilation types and also air exchange rates. And this could be because the deposition flux on the floor is 3 to 4 orders of magnitude higher than the total flux into the vertical walls and ceiling. So smaller particles can go around and stick to all kinds of surfaces, but if the particles are larger, they will sort of go down. And this flux going down flux is much higher. So, different ventilation types or different air exchange rates will allow more interaction between the flowing air and the side walls. But in terms of particles greater than 0.5, this is not important, because the rate at which they fall down is much higher, 3 to 4 orders of magnitude. So 1000 to 10,000 times higher. So it's quite high. So generally mean deposition velocity is independent of ventilation types and air exchange rates. It is generally a function of the physical properties such as density and size, which then increases as the particle size increases. Now deposition rate is also written as a deposition loss rate or deposition lot rate constant, coefficient or constant, which is another type of term used in these deposition studies. It's given as the number of particles depositing on the total indoor surface in an appropriate time, so per hour or per second, and it is given as a function of the velocities in different sites and the surface area of different sites. So this is VdV is basically the vertical deposition velocity, and AV is our vertical phase. V du is upward facing velocity and AU is the upward facing surface area. VD is the downward facing surface area. So the downward facing surface area will be the ceiling because that faces downwards. What upward facing area would be the floor because that faces upwards, and then we have vertical faces, so the four sides of wall. So how much velocity is there and how much surface area is available. We can again do this derivation. So if we have the vertical surface area, so I am just going to draw one side, and this is my vertical velocity and AV. So the actual flow is V dV times AV. Now this is my upward facing upward surface area, and this is my corresponding deposition velocity. So this would be, in this case we are talking about AU, and this would be V du, like the deposition velocity towards the upward surface, upward facing area. So V du times AU is the flux V du into this surface. Then we have the downward facing surface, so we are talking about the ceiling and the velocity is like this. So AD and V towards the downward facing. So here the flux is VDD times AD. So total flux becomes this one, VdV times AV plus VDU times AV plus VD times AV, and this is equal to a rate coefficient or a rate constant multiplied by the volume. So 1 by hour, and this will be meter cube. Then we can move this V down and get beta equal to our numerator, which is here, and denominator, which is V. So here this numerator divided by denominator. So this is basically the total flux, and this is now equated to a rate coefficient multiplied by the volume of the room. This is basically this another term, and this is the derivation. The way it is determined is that one generates aerosols in a controlled indoor chamber and measures the aerosol concentration with time. So we will generate aerosols, and then sometimes we will keep on generating, or other times one can stop generating, and then see the drop in aerosol concentration. So during this drop, so you will generate the aerosols in this case and then let it deposit to different surfaces. So the concentration will decrease because it is depositing to various surfaces, and then we can fit an exponential decay curve. So for example, a pattern could be, this is time and C, and then we have an exponential decay curve, and this can help us obtain our beta, which will be the overall deposition, beta for the overall deposition, a combination of all the surfaces. In other cases, we can, instead of controlled chamber, we can observe an actual room. And in this case, once we are looking at an actual room, we can use a mass balance model. And through mass balance exercises, we can calculate the unknown rate beta. Both the methods will give realistic values, but the value itself will depend on the chamber or the room configuration, so your volume or surface area especially. So the remedy here is people use a area weighted average deposition velocity. So here, instead of instead of having different deposition velocities for each surface, we determine one area weighted average deposition velocity. So this velocity multiplied by your vertical, upward and downward facing areas will give us the total flux, and through rearranging the equation we will get our area weighted average deposition velocities beta volume divided by the surface areas. And this sort of alleviates the configuration thing, because it is area weighted, and this velocity can now again be determined from an experiment that can be conducted either in a chamber or in a room. It is shown that the experiments generally show similar dependence on particle size. So they will say कि certain rate loss for certain particle size, certain rate loss for certain particle size, certain rate loss for certain particle size. So the change in rate loss with respect to particle size is the same, but the magnitude of the rate is different. So although the rate may be reducing, for example 20% for different particle sizes, the rate number itself can be 1000 or 100 or 10 as an example, but the decrease is always 20%. So that is what it means. The experiments are showing generally similar dependence on the particle size, but the magnitude of the coefficient may be different, and this is generally because of different experimental conditions and also the characteristics of the building. So the building characteristics and also the indoor surfaces which are available for the deposition to happen. In certain case studies, for example here, a particle deposition rate loss for indoor ultrafine particles was measured in 25 primary schools, and it was found that particles mainly were removed by deposition when the air exchange rate was less than 0.7 per hour. In experiments conducted in a typical room with a normal air exchange rate approximately 1 per hour, particle deposition on surfaces was found to remove our supermicron, so more than 1 micrometer diameter, 10 times faster than the ventilation. So we are talking about coarse particles, and as we have seen previously, they can be removed by deposition and they are more independent of the air exchange rates. Again, this rate deposition coefficient can be dependent on particle size, the airflow characteristics and also the building characteristics, which would be the surface properties, and we will look slowly how. First is particle size. So the deposition velocity strongly depends on the size, and the effect is different on the effect of different deposition mechanisms is different in different size ranges. For example, for the small particles less than 0.1 micron, Brownian diffusion plays the most important role in removing these small particles of less than 0.1 micron, whereas gravitational settling is mainly responsible for removing coarse particles, which are generally more than 1 micrometers. This is an example. So here we have ultrafine and supermicron particles are more influenced than the accumulation mode particles by the deposition processes. So here we have the accumulation mode particles approximately around 0.1 micron, and you see the deposition rate coefficient is low, 0.03. When we go to the ultrafine, less than 0.1 more towards 0.05, the deposition rate coefficient is 5 times higher, 0.15. And when we go to coarser particles, it is even higher. For 1.5 it is 0.3, so 10 times higher than the accumulation mode, 2 times higher than this ultrafine. And when we are looking at 5 micrometer, it is just very high, 18 per hour. So it is almost 60 times higher than even 1.5 micrometer. So we can easily see that the accumulation mode particles have the lowest deposition rate, and then we have some higher deposition in the ultrafine and much higher in the coarse particle range. So when we have this deposition happening, as we can see, the deposition is more high in this ultrafine and coarse range, which means the accumulation particles will remain in the air. So the deposition processes will reduce the levels of Indo particles in terms of both number and mass, because mass and numbers for these, and it changes the Indo particle size distribution towards accumulation mode. Basically, we have removed the ultrafine and the coarse particles, and the accumulation remained in the air. So the particle size distribution is moved towards accumulation mode, because we have more accumulation mode particles remaining in the air. So that was the influence of particle size. The other is the airflow characteristics themselves. Generally, increased air motions will increase the deposition loss rates for the ultrafine and coarse particles on vertical and downward facing surfaces for ultrafine, and the upward for the coarse particles in our case. For the small particles with high fan speeds, almost up to 4 times deposition was observed, because due to high fan speed there is more contact of air with the surface. So our ultrafine particles will attach more to the surface, and they will have higher loss rate. So that's the speed of airflow. Then also the pattern is important. So deposition of indoor aerosols on surface also depends on the indoor flow pattern. More deposition loss was observed when the inlet outlet location changed from top to bottom top, almost 2 times for small particles. So if inlet is top and outlet is top, this is our airflow. Perhaps less chance of impaction of air with the wall, but in the bottom top configuration, the air is going and maybe there is more chance of colliding with the surface. So therefore more chance of the smaller particles to stick to the surface. So in addition to the airflow speed, the airflow pattern also becomes important. Another interesting example is even different airflow distributions for ACs can lead to different deposition patterns. So we have central AC, which can be through the sides or the top, but the speed is generally smaller, and the pattern sometimes can be more circular, and the deposition is more towards the floor. So that's our general flow if it is coming especially from top. In the split AC, we have generally higher speeds, and mostly the split AC are installed in the wall, and they throw air more in the horizontal than completely downwards. So more particles are moved towards the wall, and therefore especially for the smaller finer ranges, ultrafine ranges, we will have more particles coming and sticking to the wall. So more particles towards the wall. Additionally, our ACs can also introduce temperature differences, and these temperature differences can also lead to our thermophoretic deposition. Although when we are comparing with the deposition or the airflow influence, the airflow influence is going to have more compared to our temperature gradients. Finally, we have the surface properties. So the deposition loss rates of aerosols can also depend on room's geometry, such as the ratio of total area of indoor surfaces to volume. So within a given room, how many surfaces are available? So the larger the surfaces, the more chance of a particle coming in contact with the surface, and hence larger the chance of deposition at the surface. So the amount of such surfaces available is important. Also the characteristics of the surface itself. Is it a very smooth surface, or a more rough surface, or a very sticky surface? And all of this will influence the deposition. Again, so even in our surface, and so the deposition depends on the surface properties and whether how is the nature of the surface? Is it downward facing, upward facing, or side facing? So deposition rate will change if the proportion of upward, downward and vertical surfaces is changed, because if we have more vertical faces or a larger vertical space, or even our furniture or anything that we have put which will increase the effective surface area available in a room. What is that surface area? Is it more upward facing, downward facing or side facing? Accordingly, different types of particles will deposit. So bigger will come down, the smaller need more, if there is more vertical space, vertical face area, then the ultra fine will be more sticking. So depending on how much we have AU, AV and AD, we will have different types of removals. So we have furnishings. So furnishings, see, the more the furniture we put, there will be more total surface area in the room. Hence, there will be a higher deposition loss rate for indoor aerosols compared to the empty room. As an example, in some studies, installation on furnishing added approximately 12 meter square additional surface area to an empty room which had 35 meter square surface area. So the overall available surface area has increased by 30%, but the deposition loss rate of submicron particles was 2 times, so 100% increase. So that is, an area increased only by, or increased by 30%, but the deposition increased by more than 100%. So installation of additional furnishings or surface area will substantially influence the overall removal or overall deposition of the aerosols. Now the effect of adding furnishings is smaller for larger particles, because larger particles are generally coming down, whereas a furniture, maybe if it's a seat, okay, it may have more area, but then the seat is sort of blocking the area of the floor. So the overall area for gravitational settling is more or less similar, and it is less influenced by the increases in vertical or downward. So in this case, actually, the ceiling, so because it's actually falling down, so it is less influenced. But ultra fine deposition can increase, because now when we have the upward facing area or side areas by furnishing, there is more area for ultra fine particle to go and deposit to. In another example, studies, it was found that the deposition velocities of aerosols on wallpaper, carpets and astroturfs were much greater than on a smoother aluminum surface. So the surface property itself is also influencing the total deposition. Then the roughness of the surface also increase the deposition, particularly with the increase in particle size. So deposition of particles with a diameter of 1.3 micrometer on the roughest surface was 5 times greater than on a smooth surface, but no significant was found for the deposition of smaller particles. So the roughness somehow also is influencing the deposition. Again, deposition rates of aerosols on test carpets was higher than on wallpapers and wall plasters, almost 8 to 20 times higher than the smooth surface. So carpet is more like a rough surface, and it is sort of influencing more the deposition. Now sometimes the effect of roughness has a much greater effect on the submicron particles, because we have larger friction velocity near the wall surface, and the rough surface may enhance the deposition velocity of the small particles. But the influence of friction and roughness on the large particle deposition was lower than the gravitational settling. So increasing the roughness increases the deposition, but not as much, because the gravitational settling itself is also very important for the larger particles.